Welcome, curious minds, to another journey into the profound mysteries of our universe. Tonight, we delve into a concept so fundamental, so utterly mind-bending, it rewired our understanding of reality itself, the quantum. Imagine a universe where everything isn't smoothly continuous, but rather made of tiny, indivisible packets. A world where energy doesn't flow like water, but clicks into place like discrete steps. Settle in, whether you're drifting off, focused on a task, or simply seeking wonder. Let's explore the bizarre and beautiful foundation of everything. Before we begin, a gentle reminder to consider hitting that like button, sharing this journey with a friend, and leaving your thoughts in the comments below. Your engagement fuels these explorations. Tonight, we embark on a journey into the very fabric of reality, a voyage to the heart of what makes the universe tick, not as a continuous, flowing stream, but as a collection of fundamental, indivisible pieces. We're diving deep into the realm of the quantum. Imagine, if you will, that everything you perceive, every interaction, every shift in energy isn't a smooth, unbroken gradient. Instead, it's more like a staircase where you can only stand on discrete steps, never in between. This, in essence, is the profound, mind-bending idea behind quantum. The minimum amount of any physical entity, any fundamental property involved in an interaction. It's the universe's smallest, most fundamental packet. This notion that a property can be quantized isn't just an abstract concept. It's a foundational pillar of modern physics. It means that the magnitude of a physical property can only take on specific, discrete values. Think of it like this. Your car's speedometer doesn't have to show every single minuscule increase in speed. It jumps in whole numbers. But in the quantum world, these jumps are not just for convenience. They're intrinsic to reality itself. These values aren't arbitrary. They're always integer multiples of one single quantum. Let's bring this down to something more tangible. Take light, for instance. We often perceive light as a continuous wave, flowing gracefully through space. But at its most fundamental level, light isn't a wave at all. It's made up of individual packets, tiny bundles of energy. Each of these bundles is a photon, a single quantum of light of a specific frequency. When you observe light, you're not just seeing a wave. You're witnessing the arrival of countless, discrete photons. And it's not just light. Any form of electromagnetic radiation, from radio waves to gamma rays, is similarly composed of these energetic quanta. Consider the electrons orbiting an atom, the very particles that make up the atoms of your body, the air you breathe, and the stars in the night sky. Within an atom, an electron isn't free to possess just any amount of energy. No, its energy is also quantized. It can only exist in certain discrete energy levels, like planets orbiting a star at very specific, predetermined distances. An electron cannot exist between these energy levels. It can jump from one level to another, absorbing or emitting a quantum of energy in the process, but it can never reside in the void between. This quantization of electron energy is precisely why atoms, and indeed all matter, are stable. If electrons could spiral inward, losing energy continuously, atoms would simply collapse, and the universe as we know it would cease to exist. The discrete nature of these energy levels acts like a set of invisible, atomic guardrails, preventing collapse and ensuring the enduring structure of everything around us. It's a remarkable testament to the universe's elegant design. The concept of quantization isn't just a quirky detail. It's one of the cornerstones of quantum mechanics, a much broader and more profound branch of physics that fundamentally reshapes our understanding of the universe. The way energy interacts with matter, the very dance of elementary particles, is governed by these principles. Quantum electrodynamics, for example, is the theory that describes how light and matter interact, and it relies entirely on the quantization of energy. It provides the fundamental framework for understanding and describing nature at its most granular level. But where did this revolutionary idea come from? When did humanity first glimpse these discrete packets of reality? The modern concept of the quantum, as we understand it today, has a surprisingly precise birth date, December 14th, 1900. On that fateful day, a German theoretical physicist named Max Planck reported his groundbreaking findings to the German Physical Society. He was grappling with a persistent and perplexing problem in theoretical physics, explaining the spectrum of light emitted by a black body, an idealized object that absorbs all electromagnetic radiation and then emits it. Classical physics simply couldn't get it right. Its predictions diverged wildly from experimental observations, especially at shorter wavelengths. Planck, in a desperate attempt to bring theory into agreement with experiment, introduced a radical, almost accidental postulate. He showed that by modeling the harmonic oscillators within the black body, tiny theoretical resonators that absorb and emit radiation, as having discrete energy levels, the problem resolved itself perfectly. It was a mathematical trick, a desperate measure, to make the numbers match. Now, it's important to note that when Planck first presented his findings, he didn't use the term quantum in the way we use it now. For him, the term elementar quantum referred to what we now call the elementary charge, the smallest unit of electric charge. For the smallest unit of energy, the true energy packet that allowed his calculations to work, he used the term energy element or energy element. He didn't initially grasp the profound implications of what he had stumbled upon. He thought it was a mathematical tool, not a fundamental property of reality. But the seed had been planted. Shortly after his initial report, in a paper published in the prestigious Annalen Physik, Planck refined his ideas. It was here that he introduced a constant, a fundamental number that would forever be associated with his name, the constant h. He termed this h the quantum of action, or elementis workings quantum. This constant, now universally known as the Planck constant, became the fundamental scaling factor for these discrete energy packets. It dictates the size of the smallest possible unit of action, linking energy and frequency in a way that would change physics forever. In this same paper, Planck also provided more precise values for other fundamental constants, like the elementary charge and the Avogadro Laszment number, further cementing his contributions to the scientific community. It took time for the revolutionary nature of Planck's discovery to be fully appreciated. It was only after his theory was rigorously validated by subsequent experiments and further theoretical developments that its true significance became clear. In recognition of this monumental insight, Max Planck was awarded the Nobel Prize in Physics in 1918, not just for a mathematical fix, but for his profound discovery of the quantization of energy. He had, almost reluctantly, opened the door to an entirely new understanding of the universe. However, it was another brilliant mind, a young and audacious Albert Einstein, who truly began to understand the radical implications of Planck's work. In 1905, in what would be one of his annus mirabilis papers, his miracle year, Einstein took Planck's concept a critical step further. While Planck had initially viewed the quantization as merely applying to the emitters of radiation, Einstein boldly suggested that electromagnetic radiation itself exists in spatially localized packets. He called these packets quanta of light, or Licht quanta. Einstein wasn't just rehashing Planck's math. He was proposing a profound shift in how we understand light. He used this hypothesis to elegantly recast Planck's treatment of the blackbody problem, not just explaining the radiation spectrum, but also providing a stunning explanation for another perplexing phenomenon, the photoelectric effect. Philip Leonard's experiments on the photoelectric effect had shown that when light shines on a metal surface, it can eject electrons, but only if the light's frequency is above a certain threshold, regardless of its intensity. Classical wave theory couldn't explain this, but Einstein's light quanta provided the perfect solution. Each photon carries a specific amount of energy, and only if that energy is sufficient can it knock an electron free. More intense light simply meant more photons, but if each individual photon lacked the necessary energy, no electrons would be ejected. It was a moment of pure genius, a moment when the idea of light quanta moved from a theoretical convenience to a fundamental reality. Soon after Einstein's groundbreaking work, the term energy quantum was formally introduced for the quantity h nu, where h is Planck's constant and nu is the frequency of the radiation. This simple mathematical expression became the bedrock for understanding how energy is exchanged at the quantum level. While quantization was first undeniably discovered in electromagnetic radiation, in the realm of light and other waves, it quickly became clear that it describes a fundamental aspect of energy that isn't just restricted to photons or light. It's a universal principle. The profound insight, born from Max Planck's initial postulate, was that energy is not continuous. It is absorbed or emitted in discrete packets or quanta. This isn't just about how light behaves. It's about how everything in the universe, at its most fundamental level, operates. It's about the very granularity of existence. This journey into the quantum realm, into these discrete packets of the universe, is just beginning. We've laid the groundwork, introduced the key players, and started to grasp the profound implications of this revolutionary idea. But the story of the quantum is far from over. In our next segment, we will delve deeper into Max Planck's accidental revolution, exploring the fascinating details of his discovery and the initial reluctance, even his own, to accept the radical truth he had uncovered. We'll trace the intellectual currents of the time, the puzzles that physicists were grappling with, and how Planck's work, born out of desire to reconcile theory with experiment, ultimately shattered the classical worldview and ushered in the age of quantum mechanics. So, settle in, relax, and prepare to venture further into the strange and beautiful story of the quantum. The modern concept of the quantum, a notion that has reshaped our understanding of reality, didn't emerge from a grand pronouncement or a sudden, brilliant flash of insight. No, it crept into existence, almost accidentally, through the meticulous and somewhat reluctant work of a German theoretical physicist named Max Planck. His journey into the heart of the quantum realm began not with a desire to revolutionize physics, but to solve a deeply troubling problem known as blackbody radiation. Imagine, if you will, a perfect absorber and emitter of radiation, a theoretical object known as a blackbody. When heated, this object glows, emitting light across a spectrum of wavelengths. Classical physics, with its elegant equations and continuous predictions, struggled to explain the observed distribution of this radiation. At lower frequencies, the theories worked reasonably well, but as you move towards the higher ultraviolet frequencies, the classical models predicted an infinite amount of energy being radiated. This catastrophic divergence was aptly dubbed the ultraviolet catastrophe, and it was a gaping wound in the otherwise seemingly complete edifice of classical physics. It was as if the universe itself was whispering a secret that our current understanding simply couldn't decipher. Enter Max Planck, a man of profound intellect and a conservative nature when it came to scientific theories. He wasn't looking to overturn the established order, but rather to find a mathematical trick, a clever workaround, to make the numbers add up. In the twilight hours of December 14th, 1900, he presented his findings to the German Physical Society, a moment that, unbeknownst to him at the time, would forever alter the course of science. Planck proposed a radical, almost desperate hypothesis. He suggested that the energy of the oscillating atoms within the walls of a black body wasn't continuous, as classical physics assumed, but rather came in discrete, indivisible packets. He didn't call these packets quanta in the way we understand it today. Instead, he used the term energelement or energy element for the smallest unit of energy and elementar quantum for what we now recognize as the elementary charge of electricity. It was an idea born not from conviction, but from the sheer necessity of making the equations fit the experimental data. He had to introduce a constant, a fundamental constant of nature, to bridge the gap between theory and observation. This constant, now famously known as Planck's constant and denoted by the letter h, was initially seen by Planck himself as a mathematical artifice, a temporary crutch to solve a specific problem. He described it as the quantum of action, a term that hints at the profound implications that would later be uncovered. The idea that energy could only be absorbed or emitted in these tiny, quantized packets was deeply counterintuitive. It was like saying you could only buy sugar in 1-pound bags, never a quarter-pound or 2.5 pounds. The implications for a universe that had always been perceived as smooth and continuous were enormous, even if Planck himself initially resisted fully embracing them. In his subsequent paper, published in the esteemed Annalen Physik, Planck refined his ideas and even provided more precise values for the elementary charge and the Avogadro-Schmidt number. He laid the groundwork for a new understanding of how energy and matter interact, a framework that would eventually blossom into the full-fledged theory of quantum mechanics. For his groundbreaking, if initially reluctant, discovery of energy quanta, Max Planck was awarded the Nobel Prize in Physics in 1918, an acknowledgement of the profound impact his accidental revolution had on our perception of reality. Planck's initial discomfort with the implications of his own work highlights a crucial aspect of scientific progress. Sometimes, the most profound breakthroughs emerge from unexpected places, driven by the need to reconcile discrepancies, even when the implications seem to challenge our most fundamental assumptions. He didn't set out to dismantle classical physics, but in solving the blackbody problem, he unwittingly lit a fuse that would ignite a quantum revolution, paving the way for a deeper, more nuanced understanding of the universe, where the very fabric of existence is woven from discrete packets, from the smallest flickers of light to the stable orbits of electrons within atoms. This quantization, this fundamental discreteness of energy, wasn't just a clever mathematical trick for blackbody radiation. It was, as we would later discover, a universal principle. While Planck introduced the idea to explain the behavior of light, it quickly became clear that this concept of packets applied to much more than just electromagnetic radiation. It was a foundational piece of the puzzle, a hint at the strange and wonderful rules governing the very small, the rules that would eventually redefine what we thought we knew about energy, matter, and the fundamental nature of the cosmos itself. The stage was set for others to pick up the torch, to explore the profound consequences of Planck's accidental revolution, and to truly unveil the universe in discrete packets. As the 20th century dawned, a new and radical idea was taking shape, one that would redefine our understanding of reality itself. Max Planck had, almost reluctantly, introduced the concept of discrete energy packets to resolve the riddle of blackbody radiation. Yet, the full implications of this quantization were far from clear. It was a young, audacious patent clerk, Albert Einstein, who would seize upon Planck's mathematical curiosity and transform it into a cornerstone of modern physics. In 1905, a year that would become known as Einstein's Annus Mirabilis, he published a groundbreaking paper titled On a Heuristic Point of View Concerning the Production and Transformation of Light. Within its pages lay a concept so revolutionary it would challenge the very notion of light, a phenomenon long understood as a continuous wave. Einstein proposed that electromagnetic radiation, light itself, did not propagate as an unbroken ripple, but rather as spatially localized packets, discrete bundles of energy he daringly called light quanta, or lit quanta. This seemingly simple idea was profoundly subversive. For centuries, experiments by Thomas Young and others had firmly established the wave nature of light, demonstrating interference patterns and diffraction that could only be explained if light behaved like a wave. Yet, Einstein looked at a different set of perplexing experimental results, particularly those related to the photoelectric effect, and saw a deeper truth. The photoelectric effect, meticulously observed by Philip Leonard, showed that when light struck a metal surface, it could eject electrons, creating an electric current. But there were strange, inexplicable rules governing this phenomenon. First, Electrons were only emitted if the light reached a certain minimum frequency, regardless of its intensity. A very dim, high-frequency blue light could eject electrons, while an intensely bright, low-frequency red light, no matter how strong, could not. Second, the energy of the ejected electrons depended only on the frequency of the light, not its intensity. A brighter light meant more electrons were ejected, but each electron had the same individual energy. And finally, the emission of electrons was instantaneous, with no discernible time delay, even with very faint light. Classical wave theory struggled to explain these observations. If light were a continuous wave, then its energy should be spread out. A brighter light, meaning a wave with greater amplitude, should impart more energy to the electrons, allowing even low-frequency light to eventually build up enough energy to eject them. And there should be a delay as electrons absorb enough wave energy to break free. None of this matched reality. Einstein's light quanta offered an elegant, albeit radical, solution. He posited that the energy of each light quantum, or photon as it would later be called, was directly proportional to its frequency. This relationship was quantified by Planck's constant, h, meaning the energy of a photon was E equals h nu, where nu is the frequency. Imagine light not as a gentle, continuous stream, but as a shower of tiny, energetic bullets. Each bullet, or photon, carries a specific amount of energy determined by its color or frequency. When a photon strikes an electron in the metal, it either transfers all its energy to the electron or none at all. There's no partial transfer. This all or nothing interaction immediately explained the photoelectric effect's mysteries. If a photon's energy, h nu asterisk, was less than the minimum energy required to liberate an electron from the metal, a threshold known as the work function, then no electron would be ejected, no matter how many low-energy photons hit the surface. This accounted for the frequency threshold. A blue photon, with its higher frequency, carried more energy than a red photon. If the blue photon had enough energy to overcome the work function, it would eject an electron. The red photon, even in vast numbers, would simply not have enough individual energy to do so. Furthermore, the energy of the ejected electron would be the photon's energy minus the work function. Since the photon's energy depended only on its frequency, the kinetic energy of the emitted electrons also depended only on the light's frequency, not its intensity. A brighter light simply meant more photons were hitting the surface per second, leading to more electron ejections. But each individual electron would still carry the same energy if the frequency remained constant. And the instantaneous emission? That was also explained. If a photon had sufficient energy, it would instantly transfer it to an electron, which would then be ejected immediately, with no need to accumulate energy over time. Einstein's light quanta hypothesis was a profound conceptual leap. It suggested that light, while exhibiting wave-like properties in phenomena like diffraction, also behaved as if it were composed of discrete particles when interacting with matter. This duality, where light could be both a wave and a particle, was utterly counterintuitive but incredibly powerful. It laid the groundwork for the concept of wave-particle duality, a central tenet of quantum mechanics that would eventually be extended to all matter. At first, Einstein's idea met with considerable resistance. Even Planck himself was skeptical, viewing his own elementar quantum as a mathematical trick rather than a fundamental reality. The prevailing classical view of light as a continuous wave was deeply entrenched. Yet, the empirical evidence from a photoelectric effect was undeniable, and Einstein's explanation was elegant and consistent. The implications of Einstein's work extended far beyond just light. By proposing that energy itself comes in discrete packets, he solidified the revolutionary notion of quantization. This wasn't just a quirk of electromagnetic radiation. It suggested a fundamental aspect of how energy interacts with matter at the most minuscule scales. It showed that energy could not be absorbed or emitted in arbitrary amounts, but only in specific quantized steps. This concept of quantization, first hinted at by Planck, and then dramatically confirmed and expanded by Einstein, became one of the foundational pillars of quantum mechanics. It provided a framework for understanding not only light, but also the behavior of electrons within atoms. The fact that electrons can only exist in certain discrete energy levels within an atom, rather than a continuous range, directly stems from this principle of quantization. This is why atoms are stable. Electrons cannot spiral into the nucleus because there are no available energy levels below their lowest allowed state. Einstein's light quanta ultimately led to the development of quantum electrodynamics, a theory that describes how light and matter interact, forming the most successful and precisely tested theory in all of physics. It's a testament to the power of imagination and the willingness to question long-held beliefs, even when the evidence seems to point in a different direction. The journey from Planck's initial reluctant introduction of discrete energy packets to Einstein's bold assertion of light quanta marks a pivotal moment in scientific history. It was the moment when the universe truly began to whisper its quantum secrets, revealing a reality far more intricate, discontinuous, and astonishing than anyone had previously imagined. This new understanding not only explained baffling phenomena, but also opened up entirely new fields of inquiry, inviting us to delve deeper into the fundamental nature of energy, matter, and the very fabric of existence itself. And it all began with the daring idea that light, that seemingly continuous flow, was, in fact, made of discrete, indivisible packets, forever changing our perception of the cosmic dance between light and all that it illuminates. And so, we conclude our exploration into the mesmerizing world of the quantum, a realm where reality is stranger and more magnificent than we could ever have imagined. From Planck's reluctant genius to Einstein's audacious vision, the journey of understanding the universe's most fundamental units continues to inspire awe. Thank you for joining me on this deep dive. If this narration resonated with you, please consider liking this video, sharing it with those who seek wonder, and subscribing to the channel for more voyages into the scientific unknown. I'm always eager to hear your thoughts. What part of this quantum journey fascinated you the most? And what cosmic or microscopic mysteries would you like to unravel with me next? Until our next shared exploration, keep wondering, keep learning,